Hey, hi YouTube. This is Nikhil. I'm a master's student at Johns Hopkins, and I am doing my research on multimodal understanding, particularly low resource domains like surgery, and I'm also working on human AI interaction and also on cross-lingual understanding. And so, with some of the research that I'm doing, and in general as well, I read a lot of research papers, and I usually also have to present them. And I just thought, like, I might start uh, sharing these. Not particularly, I'm not thinking that this might, like people who are interested might see them, but this is more sort of for myself. I can in the future go back and look at the videos that I've created and just get a quick overview. But hopefully, this is also something that uh, people in general can benefit from. And I make some of these videos already, and I usually keep it for myself. But I just thought I might just make it open source because some of these papers are quite niche, and uh, it might um, help someone along the way. I going to I'm gonna be gonna tend to make this shorter or longer. Short videos will be mostly just brief overview. If it's a paper that I feel really deserves a lot of time, then I'll create an in-depth 30-minute video walking through the math, and also creating maybe coding it as well. If the code is not there, walking through the code if it is there. And yeah, so this is my plan. And I'll cover some of the basic stuff as well. Just because it's really good to have a good foundational understanding for me as well while making these videos. I feel like I I tend to understand these concepts better, and uh, so yeah, uh, that's it. And well, let's get started. So today's paper is a paper that I was looking at for one of my researches in surgical QA, and so I came across this paper. It's quite recent paper, at least as of now. So it's Surgical-VQLA. So basically, starting off with the brief problem statement, right? So, what usually happens is these surgical VQLA papers are usually created for residents, medical residents, and it's for them because they usually ask questions to experts, and experts don't have the bandwidth to answer those questions always. And experts, as is, are like really their time is already really valuable, and hopefully some of these questions that are redundant and are asked a lot and are quite obvious to answer can be answered by these language models or vision models or hybrid. So uh, yeah, so this paper talks about, like, currently they people are not don't utilize this. They did a survey, and the residents are not particularly utilizing this well, and I agree. Like the systems right now are really rudimentary, and I am working on a similar task, and these models can't really answer why, or some of the niche questions that these residents tend to ask. And currently their utility is there is no utility. So it's a quite interesting problem, especially because, again, the data. Because let's say I'm from Hopkins, we have our data, but we won't be making it public. So similar hospitals have their own data. They usually don't make it public, and just because of privacy and some of the compliances that that need to be made. Um, and so that's the problem, right? Data. I mean, if we had as much data as is there, we had a world wide web full of data about these surgery, as we wouldn't be talking about these, because then it would just be a simple matter of large language models and or large models, large vision models, large multimodal models, and these would be able to handle them perfectly. The problem arises when you have a low resource setting, uh, and because number one, these images, the models have not seen these images, and these kinds of images, the questions in medical in medical domain are pretty fine grained. It's very pinpointed. You need very accurate answers, and yeah, so usually it's really difficult to achieve a, a model that could provide good utility. We are not there yet. So what this paper basically is trying to do is it's saying, well, let's just scratch why, right? So why we are taking a big leap to why we are not currently able to answer the what and where itself. You know, so they say that the why can be inferred from what and where. I I think that's a very uh, naive way of thinking, but it is still, I do understand where they're coming from, and it is a first step. So so that's what they do. They just decompose. They try to accurately answer the what and where, and that's how they have created this model. So jumping on to the problem itself, right? So what is the problem? So the problem is usually like the conventional VQA models. What they do is they have um, this feature extractor that's running first, right? So they extract the features. They have sorry. So they have the object detector running first. So they first already have the bounding boxes, all the bounding boxes that they need to identify, and then they pass it to the feature extractor, and then they predict the output. Um, so um, so so the problem is with this part, right? So as when they were doing their research, and this is again before the segment anything model that came out of Facebook, right? uh, this process of segmentation was not solved, especially in a low resource domain such as medical domain, and there were a lot of errors. There was a lot of computational computational overhead, and that's why this initial step itself, if you have error here, that would be propagated towards the VQA model, and so their main target was this then. So they're like, well, we don't need this, right? We don't need this here. Let's just take the question and the image, feed it to the feature extractor, and parallelly predict the bounding box and the output. Now, this gives us the answer to the what and the corresponding where. So the answer is localized. Um, this is a really I like this way of thinking. I do agree that this part is an overhead and computationally, and also like any errors here would propagate further, and traditional segment anything models sorry segmentation models were not that great. um, Sam is. So I've done some preliminary studies, and some of my colleagues also have done some preliminary studies on SAM, and it works quite well on surgery. So I am interested in seeing what the results are when this particular step is performed with SAM, and how much better would this get, this particular flow. Um, but for now, ignoring SAM, this is what they intend to do. And basically, how they do this is they have this image and a question. So they run the image through a feature extractor. They get the visual features. They tokenize the question, create add positional plus segmentation embeddings. Again, here as well, they add the positional plus segment embeddings, and they create a visual embedding. They create a word embedding here, and this is where their innovation is, the gated fusion, where you can think of this as sort of a gate, where what it's basically doing is, you pass the visual embedding and the word embedding through a tanh function, and alpha is the control here, which sort of, uh, in layman's terms, would predict, well, do I give, for this particular question, should I give more priority to the visual features, visual embeddings, or the word embeddings? And so basically that's what it's doing. And why do they do this? Well, it's because, this is another point that they raised in this paper, is uh, the current way of concatenating or mixing the word embeddings with visual embeddings is very rudimentary, and it's basically, it's not robust. It's not, it's a very naive way of thinking, right? So basically what usually happens is, you take the visual embeddings, you have the word embeddings, you concatenate them. Here they have a gated fusion, which should ideally be more effective in getting an ensemble of these word and visual embeddings. And then they pass it through a pre-trained VIT. This is the vision transformer block. And now this is another thing that they have, that's that's unique, that they have a parallel classification and localization head. So the classification and the localization are both happening at the same time. So you have the class and the label predicted at the same, the class and the bounding of that class provided at the same time. So ideally, this should give more accurate results than if you were to feed, the way you were to pre compute the bounding boxes and then feed it to the feature extractor. So in a sense, this is their method. And going through the maths, I mean, this is basically, this is a concatenation of the features, and the F here is, I think, the visual embeddings, and E is the word embeddings. Theta W, theta F, theta E, all these are learnable parameters. So the W is the one that's, this sort of the gate, right? W and 1 minus W, this corresponds to here, W 1 minus W. And uh, so this final thing here, this is the final output, which would be the GVLE. Um, and so for the loss function as well, they employ GIOU loss, and as well as the L1 loss. So this is for the bounding box, and this basically here, what it means, like how much overlap there is with the bounding box that should have been present area wise. And I think they did a bunch of experiments with different loss functions, and I think this is the one that got the most accurate results. And LCE here means basically, the classification error, uh, the loss of the classification error. So Again, the data set here is EndoVis 18VQLA and EndoVis 17VQLA. Basically, so these are MICAI endoscopic vision challenge from 2017 and 2018, and they have described the data set. They created they have annotated the frames with question answer and bounding box themselves. So and they have published it online, so in the GitHub. So that's how we can use this. Um, and they have provided some results of their implementation detail with the optimizers and the framework that they used. Um, Now, looking at the results here, we can see that EndoVis 17 BQLA, this is the 17 one, this is the 18 one. So basically, like before we look at the results, here is basically what the data looks like, right? So the red one, the red, I think the bounding box, that's the ground truth, and the answer is idle. And yeah, so basically, the question is, what is the state of bipolar forceps? Mm, and as you can see, like here, GVLE, LVIT gives consistently better answers. Again, this would be very cherry picked, right? But yeah, so they compare their results with Visual But with ResMLP, and so these are the some of the configurations of these models. And as you can see, mostly for the object detection tasks, it performs all right. It performs better than a lot of these other models, not by a significant amount. It's 3 to 4%, 2% increment, which is all right. This here, again, it's all right, but it's again, it's not too big of an improvement. But I think overall here we can see that like GLB consistently outperforms. This is I think the VLQA K4 comparison, and yeah. So overall, um, I think that and they have made their case on, like, they have done significant studies that I am convinced that their method is better. They have considerable ablation studies as well. Uh, they have done considerable amount of experimentations. So uh, I give props to them. They definitely have sold me on that their method does work. But coming back to the data set, right? Again, as you can see, this is more sort of a classification data set. I mean, it's sure it answers the what and where, but this is still a long leap from why. And the problem, so again, a point to note here is that this is a VQA task, right? Vision plus question. Now, VQA, that that narrows down the the tasks that it can handle, and this particular setup of VQA, especially like I'm talking about this from a similar challenge of answering why, right? You cannot tackle it from VQA alone. I mean, it's an interesting point to think about, like what are the tasks that can be handled through VQA, and what needs a more sophisticated sort of setup, because uh, as soon as you get VQA, there are two problems that arise. The number of tasks that you can handle goes significantly. It significantly goes down. There are fewer tasks that you can handle with VQA, because you need the question. Your question is grounded in the visual part, and also the second problem is that the data set, weak having a VQA data set, it's more difficult than having a, let's say, a vision or a text data set. And since we have large language models, we can be more flexible with having a vision part and having a language part uh, separated, and that's currently the approach that I'm using. I do not intend to change that for at least right now. I So there's a vision, there's sort of a vision VQA task, and then you pass it to a language only task, and that gives me more flexibility to handle more edge cases. Um, so yeah, I don't know if I ran long, but this is my first video, and hopefully I can. I get better over time. And again, I'm not an expert in all of this. I am just learning this as you are as well. So there might be statements that I made that might not be accurate, and I would definitely be open to discussing them with whoever comes across this video. Um, and yeah, so that's it for today. And next time I'll do another paper. I think I have one for that's in human computer interaction that I have been planning to get off my checklist, so I'll probably be doing that. So if anyone watched this till the end, thank you so much, and see you next time.